Hello, my name is Ben Weisenberger. I'm an application engineer with PROLIM PLM, and today we're going to be taking a look at Solid Edge in action. This is a nice summary of what Solid Edge is, the complete portfolio. Not only does it offer rich design solutions, but also simulation, manufacturing, and design management. If you need anything on top of that, there are also lots of add-in apps, integrations to the best-in-class solutions. So to introduce you to Solid Edge, I'm going to take you on a first look tour. And the product we're going to work on is from a customer master mover. Their products are all about moving heavy loads easily, whether it's a boat, wind turbine, or even a London bus. The model we're going to focus on today is for lighter duty loads, but the idea is the same throughout the range, a clamping mechanism which transfers the weight of the load onto the axle for traction, ready for injury-free, easy load moving. And as we can see, these electric tugs are used all over the world in well-known companies such as Aston Martin, Cadbury, and even Siemens. Now, it doesn't matter that you don't design these same products. I show this to anyone regardless of their industry, and what we want to focus on is how Solid Edge works for day-to-day activities, forming a foundation before we go into anything more specific. This is the workflow we'll follow: part design, part drawing, data reuse, assembly design, assembly drawing, and then finish off with a quick strength test. Here's the master mover we can see on the right that we're going to work on, and the project in hand is redesigning this clamp arm from scratch to suit a product update. First up is part design, and what I want to focus on here is something that's a real differentiator in Solid Edge, and that's synchronous technology. Now, rather than dismissing this just as some sort of buzzword, let me introduce why Siemens created it. The most common type of CAD system available in the marketplace uses what's called history-based modeling because it has many great benefits, such as being dimension-driven. It's so good, in fact, that Solid Edge has been history-based modeler for about 20 years now and continues to provide this method today. However, we've worked this way for so long that we've learned to ignore some of the not-so-good things, such as having to pre-plan the model. Looking for a better way to work, we can turn to direct modeling because this has some great benefits such as direct interaction with the model, but there are downsides to this method as well, such as being featureless, so not very organized. So how about taking the best of both worlds, but leaving out the downsides? Well, this is why Siemens created synchronous technology, with unique items such as 3D driving dimensions and face relationships to really synchronize those worlds. In fact, the technology is so unique to Siemens that the last time I checked, there are about 8 patents granted, with a further 23 pending. Obviously, it's much more exciting to see this in action, so let's do just that. So here we see the master mover assembly, and we're going to start by designing our part using a top-down modeling approach. To do that, we're going to kind of narrow down the parts that we can see here using a display configuration, and we're going to edit into one of these sub-assemblies so that we can design the part in the context of that assembly. What we're going to do is simply define where we want to start that component by using some of the existing geometry from the components in the subassembly. And then using the Solid Edge data management, we can come in and automatically assign things like a document number to the new part file. We can also go in and browse and choose where we want to save this part, in our case out to our working directory. We can add other relevant information, things like titles or notes or whatever else we might need. Simply hit save, and now we've started our new part file. Again, we're editing this or designing this in the context of the assembly, so to start to create some of our features, we're simply going to reuse geometry from the surrounding or adjacent components. In this case, we'll reuse this face geometry here and simply extrude that out, and now we've got our part started. We didn't have to go in and create any sort of sketches to begin with, anything like that. We just go do it and start to create the geometry. Next thing what we might want to do is start to maybe cut away some of the geometry. Again, I'm just going to start directly interacting with the model using synchronous in our steering wheel to push those faces through the model to create a cutout. Also, if we maybe want to add some geometry, we can select a face here, pull that face away from the model, and key in a specific distance if we need to. We also have the capability, if we do want to sketch something, I can come in here and maybe simply just draw a line somewhere across the top of this face, which divides that face into separate regions that I can come in and select, and then simply push or pull, and based on the direction I move my cursor, Solid Edge will automatically add or remove that geometry for me. I want to go up a set distance here, and I don't actually have to type this calculation outside of Solid Edge. I can do it right here in the value box, something like 150 millimeters minus that existing 37 millimeters of geometry we already have to end up with our part here. Next thing we want to do is add some round features to some of the edges on the model to start to kind of finish this off a little bit. Notice how powerful this is. We can simply add the rounded features through the model, and we have a lot of other options that we can go through here to quickly add rounds to the other faces, and just like that, we've rounded off the model. Next, what we'll do is directly interact with the model to add some constraints and dimensions to it. I don't have to go back to any sort of sketch or anything like that. I can come in here and directly interact with the model, add this dimension onto it, and actually drive the model. This is one of the benefits of that direct modeling comparison that we saw earlier, is being able to directly interact with the geometry. So here I can add this dimension and then drive it just by scrolling my scroll wheel up and down to change that value to whatever we want. In our case, maybe we want to set it to around 45 millimeters, and then we can fully lock down that dimension so that it doesn't change on its own. We do have to go back in and change it if we want the value to be different. Other things we can do, we can actually recognize features that don't truly exist in the history tree in the Pathfinder. I can come in and do things like recognize features or ribs or bosses or cutouts. And the great thing about this selection manager option that I'm showing you here is it also works on imported type geometry. So I could bring in a part from another CAD package, recognize some of the features on there, and then delete them or edit them or move them, whatever you need to do. In our case, we're going to recognize this cutout, and we're going to actually copy that geometry and use it over again to create a cutout somewhere else in the model. We're going to do this by using the steering wheel and simply hold down Control to make a copy. We'll rotate that around about 180 degrees, and now we have a cutout through the other side of the model here. If we need to make any sort of adjustments, we can. Maybe we want to shorten that up a little bit. I can simply grab a face, and again, using the steering wheel, push or pull that to move the geometry. We also have options where we can add relationships to the geometry as well. Similar to how you would add a sketching relationship to your 2D geometry, we can add relationships here directly onto the 3D geometry. In this case, we want to offset those two faces a set distance away from each other. That way, if we come in and move one of the faces like this, they stay a set distance away, and this whole feature moves as one piece of geometry. To continue on with our model here, we're going to add some dimensions to it. So we'll go back in and use our Smart Dimension tool here to add things like radius values or diameters. This diameter value, we want to round it off exactly to 34 millimeters, so easy enough to type that in. We can also go back in and change our dimension to add tolerances, class fits, make it a reference dimension, any of that type of information that we need pretty quickly and easily. In this case, we'll just add a couple tolerance dimensions to that. Continuing on with our smart dimension, we can dimension off the center point of our round in the middle of the part to the end of the model. Easily again push or pull that value to make a change. In our case, we're going to go about 40, and we'll do the same thing to the right side of our dimension here, the right side of our model, and drive that value out to 34. Last thing I want to do with the dimensions is dimension the width of our part. So the cool thing about this, you notice when I start to drive this, is the design intent is automatically figured out here. What our original goal was to maintain the width of the cutout all the way through the model. And Solid Edge did that for us automatically. I didn't have to add any sort of relationships or information into a sketch to get this to work. I simply added one dimension, and Solid Edge figured out that all the faces are coplanar and symmetric and should move together. I can simply key in the value that I want, and Solid Edge does the rest for me. We're going to add some mounting holes to the part as well. So we'll go up and run our hole command. The great thing about the hole command is all the wonderful options that we have here inside of the options dialog. We can go in and create basically any sort of hole that you would need, simple, threaded, counterbore, countersink. And with each subtype of these holes that we also have all the different standards. So I can create any sort of counterbore ansi or isil hole that I would need. All of these are too standard, but if you do need to make any sort of changes, you can easily come in here, customize any of the values, dimensions, thread sizes, whatever you need to do. I already have a hole set up ahead of time here, just a simple M10 through clearance hole that will create down here in the bottom right hand corner of the part. Since I already have the hole selected, I can easily start our pattern command then and create a rectangular pattern up here through the model. We'll go ahead and just switch that option over so we can evenly space those holes out 20 millimeters away from each other. Last thing we want to do here to actually edit the model is make sort of a drastic change. And if you're in a history-based or ordered environment, this would be pretty difficult to do. In synchronous, simple enough as just coming in here and fence selecting the geometry we want to edit, placing the steering wheel in an appropriate location to make this sort of edit. In our case, we want to rotate and change the angle. So I want to place it in the center point of the hole, and just like this, I can easily rotate and change the angle of the right half of our part here. And again, imagine going back in and trying to edit the sketches for this feature, for the holes and the patterns and so on, and how much work that might take to make this sort of edit. Synchronous, couple clicks and I'm done. So now that we have our design almost finalized, we can go in and start to apply things like material. So I can go into our material table here and I can browse out. We have a large library of provided materials, but you can easily go in and add your own, customize them to your needs. You can go in here and add any sort of properties that you want, anything for simulation, things like yield stress, specific heat, again, whatever applies to your materials and your models that you're creating. In this case, we're just going to grab an aluminum material here and apply it to the model. And then if we need to, maybe we want to represent some of the faces as a machined face instead of the cast material look. So I'm going to come in here and paint some of these with just an aluminum texture so that it's a nice shiny machine finish instead of that cast look that all the other faces have. We can either select individual faces, or Solid Edge will also recognize features such as our hole, or we can come in here and select our pattern to paint that off as well. So what we just saw there was how synchronous technology can drive the model with dimensions, and more importantly that there are 3D dimensions directly on the model. Models also scale well, as in they don't get slower the larger they get, an issue with history-based modelers. In addition, synchronous technology does provide a list of features for easy edits and organization, but not a fragile, interlinked web like you get in a history-based modeler. Synchronous technology will automatically maintain the inherent design intent of the model, but allows us to change our intent on the fly. We saw that we can also directly interact with the model by pushing and pulling faces. This also makes editing synchronous models very flexible, allowing you to have those light bulb moments and make changes at any time without your CAD system limiting you. To summarize, we saw the best of both worlds modeling, the best of history-based and direct modeling methods, that's synchronous technology. The robust engine behind all of this is Parasolid. This is so good, in fact, that it's used by many other CAD systems on the market. However, what you might not know is that it's owned by Siemens. But we keep the best bits for our own products. Synchronous technology is exclusive to Siemens software. Next up is creating a drawing of the part. We'll add a variety of views to clearly communicate our design, retrieve some dimensions directly from the model, and finally add further dimensions and annotations to get it production ready. We can go ahead and save our part first, and then what we're going to do is take the part over into what's known as a quick sheet template. What this quick sheet template allows us to do is take any existing part file, bring that into a drafting template, and quickly communicate some different views here that are set up ahead of time. Again, any part file could be brought in and we would get something like a front view, isometric view. We can see an auxiliary view on the side here, and also automatically retrieve some of that manufacturing information that we need. Since we spent the time placing these dimensions on the part file, why waste time recreating those here in the drawing when we can easily retrieve them and bring them over? If we need to, we can come in here and add some more annotations and information. Things like center marks can quickly be communicated on the model. If we need to add center marks, maybe at an offset angle, we can also go in and use something called a dimension axis to select multiple holes and again, maybe slightly change the alignment if they're not perfectly vertical. We can also add things like center lines a couple different ways. In our case, we'll do by two lines. Quickly select these two lines here to place a center line. Maybe we want to add one to the auxiliary view as well. Now the nice thing about the center lines is they are associated or associative to the views, so that if the views change or the geometry changes, the center line will update and change as well. If we come back down here to the front view, we can add some more information, add some dimensions here at the drafting level if we need to as well. Using the Smart Dimension command, we can go in and add things like radius values pretty easily. We can select an individual line to get a length, or we can select multiple lines and get a distance. Also, if we select multiple lines and hit A on the keyboard, we can get an angle measurement. These same dimensions can also be communicated over on something like an isometric view, if that's easier for the shop floor, for instance, to manufacture this model in. Another dimensioning tool that we have is distance between. This is really useful to create stacked or chained dimensions. So I can simply go on and select multiple elements. To get those stacked or chained, there'll be an alignment set together then that I can easily adjust and move both dimensions just by dragging one of them. Other types of annotations that we can create are things like callouts. In this case, we're going to add a whole callout, which will automatically pull specific information from the different types of holes that you attach that callout to. In this case, just a simple hole, and gives us the through information there. Some of the other GD&T type operations that we can apply to our model, things like feature control frames, or if we need to, we can also add datums to the model, and we can add a datum down here to a flat edge, datum A, or we can come up here and if we need to, create a datum B and add that even to a rounded or a cylindrical type edge. We can also add other types of views such as detail views. These are simple to apply to your model. The scale can easily be adjusted here separately from any of the other views on your drawing. Here we have a detail view, obviously, that we can then, if we need to, drag around and place at a different location, which is kind of fun to do, see that live update of moving that detail view around. And of course, you have the capability to go in and add dimensions to the detail view as well without worrying about the scaling factor messing up the true size of those dimensions. Finally, what we want to do is add a broken out section view to this model as well. This is kind of a unique, cool operation that we can do here. I can come in on one of our specific views to create a profile that I want to create for my section view here, my broken out view. And then using any of the other views on my sheet, I can choose how far through the model I want to cut that broken out section view, and then simply apply it to something like the isometric view here, again, to communicate some more information inside of our model. The last thing we want to do then is make sure we save the drawing as well. So if we go up and hit save, our data management that we have here will automatically assign the document number and revision matching that of the part file that the drawing is created from. We can validate that to make sure that we have no issues with it, and then simply hit save. So to summarize, we saw fast view creation, automated production ready dimensions direct from our 3D part with the ability to create further annotations tweaked to our requirements. And all of this is clear and accurate to the standards that we choose in Solid Edge, for example, ISO, ANSI, etc. Next thing we're going to look at is some data reuse. We're going to open up an existing DWG drawing inside of Solid Edge. We'll create a 3D model from that 2D geometry. We're also going to then edit that geometry to ensure that it fits inside of our assembly with our existing Solid Edge components. So let's take a look. To start with, we can switch back over to our subassembly where we created our part file and go ahead and close out of that part and head back to the subassembly. Now we can notice here at the subassembly level that we're missing a component here to hold this top part in place. We actually have that part though created as a DWG that we may have used in the past. We want to reuse that geometry so we don't have to waste time redesigning a new part file. So what we'll do in this case is go up and open the DWG. To find that, we're going to use our data management here to search for a file. We can search on all different types of properties and criteria. In our case, we're going to search for a specific file type. We're going to look for a DWG file. We can easily search that and we return the result down here of a DWG. I can easily double click that then to open it, and I'm just going to choose an ISO draft template here to pull that up inside of. When we open up our DWG files, obviously we can see the border and all of our views and our dimensions. So what we actually do is support layers coming from AutoCAD into Solid Edge. If we need to, we can come over and do things like hide some of the layers. We can also set up how we want fonts and colors to transition from the DWG into AutoCAD and how we want those mapped across. Now what we're going to do to get this into 3D is run a command called create 3D. We'll simply choose the part file we want to add the geometry to, select our front view and our right view. You do have the option to select as many views as you want. In our case, we're going to set a fold line where we'll fold these two views on top of each other. When we hit finish, you'll see what I mean. Our two views are brought into a part file folded on top of one another. All of our dimensions came across as well. Right now they're brown dimensions because they're not really attached to any sort of 3D geometry, but as we start to create a part here, you'll notice those dimensions will become attached. Now, the great thing about bringing these sketches into the synchronous environment is I don't have to know how far something's extruded. I can simply select one of my sketches and grab a key point on one of the other sketches. Again, you'll notice some of the dimensions start to turn blue, which means they're attaching to the 3D geometry. I can go in with my extrude command and select even an open profile here and start to extrude that out or cut that through the model if I want to continue with our part here. Now, just to go along with this, there are some additional sketches at the bottom, but we don't necessarily need those. We can actually come in and delete all the sketches from the model and get rid of them and just go in and add some of our own features to finish this off. In our case, what we'll add are a couple round features down here on the bottom of the model. We'll add a couple 30mm rounds down here. We can also go in and use some of our primitive shape commands like the cylinder command to come in here and create a cylindrical cutout without really having to create a sketch that's going to drive this, anything like that. Just create a cutout through the model. Now, I talked about some of the dimensions attaching to the 3D model. Well, let's go look what happens if we go in and make a change to one of those dimensions. I can select one of them and start to drive them using my scroll wheel up or down if I want to make a change, or I could select even an angle dimension here and again symmetrically adjust that because of design intent, picking up both sides of the model. So all of that done was automatically created for us when we brought those drawing views from the 2D over into the 3D. Now we want to go ahead and apply material to the model, so I can simply right click here and maybe we just add steel to this for right now. And this looks a lot like a sheet metal part here. But all we see in our Pathfinder right now are part features and we're in the part environment. So we actually want to go over and make this sheet metal, which is easy to do inside of Solid Edge. I can simply switch into the sheet metal environment and then go in and use one of our tools to actually transition the model from a part model to sheet metal. So if you look at the Pathfinder, you watch our protrusions turn then into a tab and a flange. And just to do a couple things to prove to you that this is sheet metal, I can come in and select our bend and actually edit the bend radius. Maybe we make that 6mm instead of 3, or I could go in and actually flatten this model, select the face I want to have oriented up in my flat pattern, and we end up with the flat of the model, which also shows us our cut size, sheet size that we need to create this. So pretty quick and easy to convert this from 2D to a part to a sheet metal document. Now, what I'm going to do is go ahead and actually save this model. Again, our built-in data management that we have here will allow us to automatically assign a document number to it. We're going to save this in our working folder. All we have to do is just add a title to the file and then save it. Something new that was added here in the latest version of Solid Edge is an option to apply costs to sheet metal files. So we have a design for cost module that's included with Solid Edge that allows us to come in here and calculate things like the number of bends, cut lengths, stamping features, and associate a cost with each one of those operations. In our case, we have an Excel sheet set up for us already that maybe was provided to us by sales or some other engineers that know how much our operations cost. So what we can do is actually copy out those costs here and paste them inside of Solid Edge, and we get a cost estimate of how much it'll cost to create this part file. So we see a rough estimate about $24, $25 to create this. We're going to come back and look at this cost in just a little bit once we make some more changes to the part. But for now, let's go ahead and close out of the part file to see how it actually fits and functions inside of our subassembly. So we can close down to the part and the drawing. We don't need that anymore. We'll head back over to the subassembly and we're going to insert that component. We can go grab it from our library. If we need to, we can use the preview to reorient it to get it closer to how we want to bring it into the assembly. Simply drag and drop and add some assembly relationships. The default part positioning tool here is our flash fit tool. Makes it really easy to grab any flat planar surfaces or cylindrical surfaces and automatically apply things like mates and axial lines. Just like that, we've got our part positioned and we can obviously see it doesn't quite match up. Our angle is not correct. Some of our slots don't match up with the bolts or screws and our other components, so we need to make some changes. First thing we want to do is measure the angle between these two parts so we know how much we need to edit the part by. So I can go in under our Inspect tab and take a measurement here between these two faces, and we can see that returns an angle of 10 degrees. So we need to rotate our sheet metal part 10 degrees up. So what I can do is actually just select that part and do an edit in place here, edit it in the context of the assembly. And what I'm going to do is simply fence select the faces that I need to drag or rotate or edit, and place my steering wheel in an appropriate location then to make this rotation. So that's the power of synchronous, simply just being able to grab the things I want to change, place the steering wheel in an appropriate location, and then simply start to rotate that and make my change. So I'm going to rotate that up about 10 degrees. And if we turn on those background components, we can see that that actually works. It matches perfectly there. So we're good to go on that edit. The other edits that we need to make are to the slot features on the side of the part. So what I can do here is, again, simply fence select the geometry I want to change, place the steering wheel in an appropriate location, and start to make an edit. You'll notice our design intent is moving all 4 slots at the same time. It's trying to keep them aligned and symmetric, which is what we want. So in our case, I'm going to just bring that up, center it up on my bolt here, and those bottom slots are good to go. To edit the top, I'm going to fence select actually the entire part to bring the whole top surface down. We'll locate our steering wheel and again bring that geometry down, and just like that we've made those changes that we needed to get the part to fit our assembly. So pretty cool that we can bring in again a 2D AutoCAD drawing, bring it into 3D Solid Edge, make it a part file. If we decide then it should really be sheet metal, not a problem. Quickly transition that over and then make some edits on the fly at the assembly level to get this to fit into our model. Last couple things we maybe want to do is add another feature. Maybe we need to add some strengthening features like a gusset in here. So this is a procedural feature where we can go in and add these parameters that are going to drive it, things like the depth and the width. I already have one set up ahead of time, so I'll simply select that one. And then we just choose where we want to place it. I want to drop it right here on the middle of this bend. So we talked about that design for cost, and we saw it was about $24, $25 before. Now we've made some changes, added some additional features. So if we take a look at our cost now, we're up to about $32, $33. So pretty cool that it'll continually update and recalculate our costs of our features as we add them into our sheet metal design here. So again, just to recap, we saw how we can bring in that legacy 2D data and convert it to easily reuse it. We can use synchronous and our history-free type modifications to save time and effort. We do also have the capability to import 3D data and do something similar. We can easily go in and reuse it, make changes to it as if it was designed right inside of Solid Edge to help us reduce some of our development costs. Next thing we want to look at is some assembly design. We want to start to assemble these components that we've created with things like fasteners, nuts, and bolts. We also want to look at placing some additional components and eliminate any interference between the parts that we might have as well. So let's take a look. So we've finished with our bracket design. We can go ahead and switch back over to our top level assembly. So we'll simply close onto the part file and that subassembly, head back over into the top level assembly here. And we're going to go in and add some assembly relationships, similar to what we did with the bracket on top there. So we'll go in through our assemble command, and again, using our flash fit option, we'll simply line up some of these holes between the components. And you'll notice as we start to add these relationships, the tubes on top actually adjust. They're a fixed length tube, but the path will automatically move and adjust to fit where the components are currently placed. And so pretty nice option there that you have available with adjustable components and adjustable tubes. So we have our components assembled here. What we want to do is add some bolts or fasteners between those components to hold them together, obviously. Now, I don't want to go in and take some measurements. How deep are those holes? What are the size of the holes? So what we have is an option called the fastener system that can actually do some of that work for us automatically. So what I'm going to do is open up the fastener system, and this is going to use our built-in standard parts database where I can go in and select individual holes or multiple holes that I want to place bolts inside of. We'll choose how far through the part we want those holes to, or those bolts to go, and it'll simply bring up our standard parts database. Inside of this database, it's going to limit our options down to the specific bolts that will fit inside of these holes. So here I can see in a DIN standard, I have these specific types of bolts that will fit inside of here. This will also allow me to go browse out ANSI standard, ISO standard, whatever it may be, to again find those specific bolts that will fit in my assembly. Once you select a specific bolt, you also have the options to go in and pick things like top stacks if you want a washer, or bottom stacks if you want a nut, whatever you may need. I already have one created here for us and saved, so we'll just go ahead and grab that, place it inside of our assembly. And there we go, just like that, we place those two bolts with the nuts right inside of our assembly, speeding up that process for us. Next thing we want to do is look at another one of my favorite commands in here called duplicate component. So if we switch our display configuration, we can see we have these different bolts placed inside of the assembly. What we want to do first is I want to put a washer on one of them. So I'm going to head over into my parts library, go into our working directory, and we have a washer here that I'm going to place inside of the assembly. Now, what you'll notice actually about this washer is one of the faces is already highlighted. This is another option that you have available inside of Solid Edge called Capture Fit, where we can tell Solid Edge to intelligently remember the relationships that have been applied to the components the first time that they were placed. That way, in the future, if you use them again, it really speeds up the process of placing them. All I have to do are select the faces I want to align it with, and just like that, it's been placed inside of my assembly. Now what I want to do is take that washer and add it to all of the other bolts in the assembly. So I can select my component and come up here and run the duplicate component command. It's a pattern type operation, so it lives up here in the pattern group. And what I'm going to say is I want to duplicate that washer from this bolt to any other bolt that I select. Or using this button up here on the command bar, I can say find all matching occurrences, and just like that, we've added a washer to all of these other bolts. So that's another option you have to help speed up the assembly process. Next we want to do is change our display configuration again, and over here in the back we can see a subassembly of a caster in the back. We only have one placed inside of here right now. So what we're going to do is edit inside of our subassembly. We're going to simply fence select the geometry that has already been placed in here. We want to use that over again. I don't want to have to bring in all these bolts, bring in all these components one at a time. I simply just want to reuse them. So what I'm going to do is place my steering wheel somewhere specific here, maybe on the center of the bolt, and simply do a copy by holding down Control on my keyboard, select the steering wheel, and I'm going to copy those components over here to the left, and we're going to say redefine those relationships to this plate in the middle of the subassembly, and just like that, it's been copied over and we're good to go. Just to prove to you that it did copy those assembly relationships, if I select one of those components and we look down here to the bottom of the Pathfinder, we can see that it did create those specific assembly relationships. So again, another time-saving operation that you have available to you. You can easily copy and move components to somewhere else in the assembly. So we'll go ahead and save those changes and close down to that subassembly. Now you'll notice on this assembly we also have this spring up here, this shock. So what we can actually do is show some analysis, some movement of how this assembly will go up and down. So I can grab this component and drag it, and as I let go, you'll notice the spring automatically updates. It's an adjustable part. So as the length of that shock or that hydraulic shock changes, the length of the spring will change automatically as well. We actually have another place over here in our top level assembly that we want to see something similar. So I'm going to actually do a show all on the entire assembly, and up here towards the front we have some similar motion that we want to take a look at. So what I'm going to do is edit inside of this subassembly. And we'll do the same thing. We'll do a drag component. We want to drag this yellow bar here off to the side. Again, you'll notice those springs update as that part moves. Now, as we drag this all the way out, you may notice we might have a little bit of interference here between the yellow component and the black ones. So what I'm going to do is run an inspection operation here to check our interference. And I want to check the interference that this yellow part might have with any other part in the assembly. And just like that, it highlights the interference between those two parts. So we need to make a little bit of a change here to get rid of that interference. To start with, I'm going to drag this component back to where it was. And then we'll go in and we'll simply edit these parts here in the context of the assembly. I don't have to waste time taking any sort of measurements, finding this specific part file and editing inside of it. I can simply select both of those radiuses, place my steering wheel in an appropriate location, and easily drag those faces down, maybe something like 5 millimeters. And just like that, our change has been made, interference has been taken care of. So just like that, we made our changes to our assembly, and it looks pretty good so far. So let's go ahead and save any of those changes that we've made. So we saw some of the automated tools that we have built inside of Solid Edge to help us speed up our assembly design process. We can easily check our assembly fit and function by using things like drag component or check interference. We can also duplicate components or clone components to help rapidly speed up the process of creating our assemblies for increased productivity. Next thing we want to look at is some assembly drawing operations. We want to create maybe an assembly exploded view, also add something like a parts list with balloons, and then talk about how we can share that information with a non-solid edge user. So let's go ahead and take a look. So we're going to start by switching over to our drawing, and what we're going to do to begin with is add a new sheet. After we add that sheet, if we want to, we can rename it, maybe call it something like assembly, since that's the view we're going to be communicating on this sheet. We can then go up and run the view wizard. This allows us to create views from existing components already in the drawing, or we can browse out, and since we're running Solid Edge data management, we can go search that directory. So I'm going to search for assembly documents, and instantly that'll bring back our result of a number of assemblies that are in our working directory. If needed, we can come up here and also type in some sort of a keyword to search on. So we're going to search on the word clamp. And just like that, we return our one result. We can see our subassembly that we're working on. So let's go ahead and select that, and we'll double click that to place the view inside of our assembly. Now with this view, what we actually want to communicate is an exploded view. So I'm going to go up into our settings, change to an exploded display configuration. We can also shade this view in so it's a little bit easier to see as well, and then we'll come down and place this on our sheet. Now with this view, we want to add a parts list. We want to see a bill of materials of all of the part files here. We also want to add balloons that will attach to some of the components as well. We can do this all within one command, our parts list command. We simply select the view we want to create the parts list of. We'll go in and create our parts list here just using a millimeter standard format that we set up ahead of time. Simply place that parts list onto our sheet, and there we go. We see our balloons and our bill of materials. If we start by looking at the balloons, you'll notice they're attached to a dashed line. That's called our annotation alignment shape. That can actually be edited. We can go in and do things like change the size of that, and notice all the balloons are attached to it and we'll move with it. We can do a shape edit or a local edit, or if we want to, we can go in and grab the balloons and slide them along the shape, or if we need to, we can also pull the balloons off the shape. So it makes it really easy to work with and get those balloons organized on your sheets. If we go over and take a look at the parts list itself, we can simply double click this and go in and make edits. We can go in here and select components in the parts list and get a preview of them over on the left. It'll highlight them in the drawing view as well. It makes it really easy to work with it. Again, if we want to do some edits, I can come in and maybe select some cells, make those bold, italicized, underline, whatever you may need to do. So now that we have our assembly view done, we want to talk about how we can collaborate maybe with some non-Solid Edge users. So what we have is an option called the Solid Edge portal. This is available inside of Solid Edge. Running through the application button, you can go directly to the portal, or you can simply go out to the website and you can create a login here. This is free to do. If you're a Solid Edge customer already, you'll have a WebKey account that you could use to log in, but you're free to go out and use another email to create an account as well. What we're going to start by doing is creating a project here, and this will allow us to then take any files that we want and upload them into the portal. So in this case, we've made a master mover project that we've uploaded some part files, assembly files, drawings, whatever it may be. We can see all the files we've uploaded, and then if we want to take a closer look at one of them, we can easily open them up. We can zoom in and out. We can see all the drawing view dimensions, annotations, anything you might have created, we can easily review here on the web in the portal. You do have the option to go in and create markups then if you need to as well. We can do things like draw shapes. We can add text like we're doing here. Whatever you need to do, it makes it really quick and easy to create different types of callouts, or maybe there's an issue in the drawing that needs to be fixed. These then get added over on the left in a Pathfinder that you can then go back and review anytime in the future and pull up those markups to see if that change has been made to the drawing or not. Here we can see an assembly on the portal. Really quick and easy to rotate these around. We can expand again the Pathfinder, see all of the parts and subassemblies listed over there on the left. We can either graphically select the parts from the assembly itself, or we can go over and highlight them from the Pathfinder. That allows us to do things like zoom on just that part file or do a show only, whatever it may be. We can quickly auto-explode these subassemblies if we want to, or we could auto-explode the entire assembly, which we'll see in just a little bit. Some other options that we have are to create things like section views. So we can create section views on the different base reference planes and drag those through the assembly wherever we may need them to be, just to take a quick look inside of the components. If we turn back on the top level assembly, maybe we'll rotate around and we want to focus on this back area over here. And similar to like what we did in the drawing, we may want to add a markup to this. So again, I can draw some sort of a shape, whatever it may be, and then go in and add some sort of text. Maybe we want to check to see if we have this part in stock or not, so that if it's not, we can go out and go ahead and order that. Just like with the drawing, this also gets saved to our Pathfinder, so we can give this call out or markup a name, and then you can see on the top left there, it appears in the top of the Pathfinder. We can select it and it'll take us right to that markup. You do have the option to download these files then if any changes were made and another user wants to download them, they can. Now, one of my favorite things to do with the portal is actually the capability to use multi-CAD. We can bring in files from any CAD package that we want and view them here in the portal. Now, just to show off a little bit here, we have a larger assembly, obviously. And what I want you to pay attention to is the speed of this. Notice how fast it is to section through this assembly, how fast it is to rotate it around, and then my favorite thing, auto explode. That's just amazing, being able to explode such a large assembly so quickly and see all of those components. Now, new with Solid Edge 2019, we have some extra electrical capabilities and extra electrical packages, so we can do things like view those PCB boards that you might design in those electrical packages here on the portal as well. We can then work with collaboration here options by giving other users the option to view and download those files if they want to, so that they can open them up in Solid Edge like we see here. Now, the portal can be basically used on any device that has internet access. So this can be done on a Surface Pro tablet like we see here with touch capability. We can go in and view those markups, or we could even do it on a cell phone. Again, anything with internet capability, we can go in and view those portal files, any assemblies, parts, drawings, markups that you might have added on there. It just really allows the non-Solid Edge user the flexibility to come in and view those files that you might have created. So we saw how easy it is to control our drawing view updates and to facilitate any engineering change orders. We could automate our parts list by automatically adding those balloons in there as well. And then we talked about the great free collaboration tools with the Solid Edge portal. The last thing we want to take a look at is our simulation capabilities inside of Solid Edge. We want to be able to virtually test our models to ensure that they meet our required strength. We also want to make any required changes to those files and retest them. And then at the end, we'll create an analysis report that we can share with a manager or other users if we need to. So let's go ahead and take a look at simulation. We're going to switch back over to our top level assembly, and what we're going to do here to begin with is we're going to edit into the subassembly where our clamping arm is. So we'll open that guy up. And we could do a simulation on the entire assembly, but what we're focused on mainly is just this clamping arm. So what I'm going to do is isolate that component for right now, and then we can go up and switch to our simulation tab. Now there's kind of two different ways we can run simulation, either across the ribbon on the top of the screen, or we can expand simulation over here on the edge bar and work vertically here in the edge bar. First thing we need to do though is create a new study. So we'll go ahead and do that. Now the different types of studies that we can do linear static, normal modes, buckling, some steady state heat transfer, or even some transient heat transfer. We're going to keep it on linear static for now. And after we select our component that we want to do the simulation on, we can then start to apply our loads and constraints. So what I'm going to do is go in and apply some forces. We have some forces that will be applied here where these two holes are. So I'm going to fence select these, and again, these are the holes where the bolts are going through our model. Now, simulation runs just inside of Solid Edge, so we have a lot of the similar tools here that we've seen already, things like the steering wheel. So I can use that to change the direction of our force on those holes. We'll increase that force to something like 250 newtons as well. Next, we're going to apply a constraint, we want to hold some portion of this model in place so that it doesn't move. So we'll simply add a cylindrical constraint down here inside of the component. And then after that, we can go in and we can mesh and solve our model. So I'm just going to do a right-click mesh here, and then that will allow us to do both a mesh and solve at the same time. You do have the options to go in if you needed to and just mesh it first and go and analyze the mesh. You can go change the size of the mesh. Maybe you need a little finer mesh around some of the holes or the rounds or radiuses, and you don't need as fine as a mesh on like a big flat open area. So you could go in and edit that if you needed to. Our case, just the default mesh will work, and there we go. We can see our simulation results. So pretty quick and easy to do. This is nice because this allows your engineers to do the simulations right here on their models as they can currently design them. You don't have to waste time sending the simulation off to another simulation type engineer and waste time doing that. Now we see our results, so we can go in and do things like animate those results. In this case, we're looking at the stress applied to it as those forces kind of bend and move that component. Now this is exaggerated, so we can go in and do things like make the actual movement. So if you look real close, you can maybe see it move a little bit, but it's not going to deflect that much in real life. This animation can easily be saved out into a video if you wanted to do that. We can also, though, change this and view things like displacement, or we can go in and view things like our factor of safety. So in our case, we want to focus on that, the factor of safety. Now our scale doesn't quite fit what we want to see here. So I can switch over to our color bar tab. We can define our own scale, and we want to do something like check out the factor of safety between 2 and 3. We'd also turn on things like a minimum or maximum marker, and we can see really here on the inside of that radius that we have a factor of safety of just about 2, which isn't quite high enough for our model. We need to be about a 3 or higher for our factor of safety across the entire model. So we got to make some changes here. So what we're going to do is close out of our simulation results for right now. We'll head back into our assembly and we're going to make some changes. Now, the nice thing again about Solid Edge is we can make those changes right here on the fly in the context of the assembly. So I can come in and simply start to grab faces, even faces from multiple parts at the same time, and then we can go in and start to make a change. Now you'll notice that we get a message here. It says some of the components are read-only and cannot be modified. So what's actually causing that is this component here has been released. So we can see that with the red check mark. We're using, again, our Solid Edge data management. That file's been released, so we can't make any changes to it. Let's do this. Let's go see if that file is actually used anywhere. So we're going to go do a where used. And just like that, we get the results of where that part file or sheet metal document has been used. We see it's existing in the current assembly that we're inside of, and then only one draft file, which is the draft file of that sheet metal document. So we're fine to go ahead and make a revision of this document because we know it's not used anywhere else. We won't have to go revise this in the other assemblies as well or anything like that. So we're good to go here. So I'm going to close out of our where used, and I'm going to go in now and create a revision. So we'll simply hit a new revision. That's going to bring up our data management. It allows me to give it a different name if I needed to, a revision number, but it should take care of most of that for us automatically. We can see it's going to move it over into our work in progress folder, and it gives us our revision number of C. We can then hit save, and just like that, the part is now released, and we can make a change. So let's go back in and grab those couple faces, and we'll start to push those up. And we just want to go up about 5 millimeters. We'll add a little bit of thickness to that. I also want to come in here and grab that inside radius, and with this one as well, we'll also just change that to 5 millimeters. So we've made our changes. Let's head back into our simulation here. So we'll isolate this component one more time, and what we're going to do is we're going to go back into our study, and we're going to solve it again. So this will take into account now those changes that we made. So it may need to do a little bit of remeshing, but then it'll go back in and solve that analysis again, applying that load that we put on those 2 bolt holes and our fixed cylindrical constraint as well. So now we can see our results. Again, we can see our von Mises stress to begin with, but we can go in and easily change that. And what we care about, like I said before, is the factor of safety. We'll do a custom scale again between 2 and 3. And we don't see any more yellow down there. So that means our factor of safety goal has been met and we're good to go. So I'm going to switch this back for now to our stress. And what we can then do is create a report of this. Maybe we will need to share this report with some other engineers or a manager or something like that. So I can quickly create a report, give this a name, add an introduction statement or a conclusion to this as well. Then we can save it down as an HTML document or a Word document. We'll hit create report. It'll go through and grab some different screenshots for us, grab some different values and put it all in a nice study or report for us here. So we can see things like the study properties. We can see what material has been applied to it, the yield stress properties of that material, what loads and constraints were applied. And then down here we see different screenshots of the different stresses or displacement values that would actually happen on our model. So a really, really nice report that gets created for us automatically from within inside a solid edge simulation for us. So that takes care of our simulation aspect of this. So what we're going to do now is close out of this and actually head over into our drawing. We've made some changes to this part document, right? We added some height to it. We changed that radius value. So we want to go reflect those changes on our drawing. This is going to take a second to save just because we're also going to save those simulation results to that part file as well. We'll jump over here then to the drawing. And if we go back to our main sheet where we had that view on here of that clamping arm, we can see there's a gray box around the views, and that indicates that the views are out of date. We can simply hit update views. That'll update all our views, and then what we have here is a tool that'll help us track any changes that have happened in the drawing. Now we can see the center line moved. We don't really care about that, so we're just going to get rid of that one. But we see that we have two other dimensions that change. So let's go find them. That allows us to zoom in and see where those are at. We can copy them if we want to as well. And we're actually going to change the revision. These are going to be revision A. So instead of being labeled 2 and 3, they're both revision A, which allows me to then come up here into a revision table. This is an embedded Word document, which you could do inside of Solid Edge. To edit this, we simply double click it, and now I have access to the document as if I was inside of Word. I can come in then and paste those values and give it our revision name. Just like that, we've updated our revision table, added all that relevant information that we need in there for what dimensions changed during that revision, and our drawing has been updated. So there we go. We created our master mover. We went and created that clamping arm. We brought in some other components, DWGs, things like that. We assembled the components, made changes to them here in the context of assembly. Also did a little bit of simulation on the parts as well to ensure the fit and functionality, assure it meets our standards as well. So with our simulation, obviously it's integrated into Solid Edge, so it makes it much easier for the designers to use. That allows us to reduce our physical prototype costs and material costs as well. And this is all done using the industry-proven technologies of FEMAP and Nastran. So that's it for the first look. We saw a breadth of capability, but I'd like to finish up on our main differentiator, which is synchronous technology and the value it brings as part of Solid Edge. So if you're going to remember three things about Solid Edge, let them be these: that we have accelerated design that allows us more time for innovation, faster revisions for quicker time to market, and better reuse for reduced costs. And of course, you don't have to take my word for all of this. As you can see, here are some of our happy customer quotes. And with that, I want to thank you for your time.